Here we have a reinforcement learning agent. Hey there, little guy. All right, let's put this thing inside of an environment. Here's a nice environment. The initial observation has 3 walls and a blue background. And now the agent's just going to start taking actions. It looks like it's seeing quite a few of these gray observations with 2 walls. Okay, now there's a purple one. Oh, and look, it got a reward. Great job, little guy. Now let's have it do another episode. This time the initial observation is red with 3 walls. And for the sake of argument, let's just assume that it keeps making the same decisions as before. Ooh, -1. Better luck next time. Alright, now imagine you're this agent and you're trying to make sense of how this world works. In the first episode, you saw a blue observation, followed by a +1 reward. And then in the second episode, you saw a red observation, followed by a -1 reward. But is that distinction important? If it is, the world probably looks something like this. 2 parallel hallways, each with a different initial observation and leading to different reward configurations. If the agent's going to do well, it's going to have to remember the initial observation all the way to the junction, and then choose the action that leads to the reward. On the other hand, the world could also look something like this, with no particular correspondence between the initial observations and the goal locations. In this case, the agent's actions transition stochastically between the different states instead of deterministically. And this world is just as good of an explanation for the agent's experiences. So, how is the agent supposed to figure out whether the world is more like the first one or the second one? Is it partially observable and the agent needs to remember the first observation to know which way to go at the junction? Or is it fully observable and the agent doesn't really need to remember anything? Actually, it turns out there's a really easy way to tell. Suppose the environment really is partially observable, and we want to estimate the agent's value function for a fixed policy. The agent's policy is going to induce some behavior in the environment, and then we can estimate the value function by just averaging over the rewards that we've seen for each observation. This is called Monte Carlo estimation. Another way to estimate value is to add our immediate reward to whatever our value estimate says we're going to get for value at the next observation. This is called temporal difference learning. And notice that these 2 different computations give different results. It turns out both of these algorithms can be viewed as special cases of the same general learning algorithm called TD Lambda, which averages together many different n-step returns. Here's how it works. When lambda equals 1, TD Lambda essentially solves for the state value function and then projects that value function into the observation space, with 1 value per observation. This is equivalent to what Monte Carlo estimation would compute. Meanwhile, when lambda equals 0, TD Lambda essentially computes the observation projection as a first step, resulting in an effective MDP, which it then solves for the state value function, which is essentially the same thing as the observation value function, because at this point, the states are already the observations. In other words, when lambda equals 0, TD Lambda essentially computes the observation value function as though the observations were Markovian states, as if the POMDP were actually an MDP. And since these computations produce different value estimates, we can actually use the difference between them as a signal of partial observability. We call this metric the Lambda discrepancy. And it turns out that this metric is actually quite reliable. If some policy has a Lambda discrepancy above 0, almost all policies have a Lambda discrepancy above 0. Additionally, if a POMDP has Markov observations, the Lambda discrepancy is 0 for all policies. And it doesn't just detect partial observability, it can also mitigate it. Consider a classic DeepRL agent whose policy is trained with proximal policy optimization, and whose value function is trained with TD Lambda. Now, normally, if we were expecting this agent to have to cope with partial observability, we would just add a recurrent neural network on the front end. But if we also add a second value function, then we can train it with Monte Carlo estimation, or any other TD Lambda, and then take the difference between the value functions to compute the Lambda discrepancy. If we then minimize the Lambda discrepancy alongside the traditional losses, it leads to a much better representation and much better learning performance in partially observable environments. Look at this Pac-Man environment where the agent's observations only show it the nearby surroundings. When we include the Lambda discrepancy as an extra training objective, the agent learns a lot faster. Look at that little guy go. Incredible. Not only that, but the representations that it learns much more accurately track where the agent's been, which is important for collecting food if you can't see where you're going. That's all we have time for right now, but for more information, check out the full paper. And thanks for listening.